All right. In this video, I'm going to overview the background sections of Lab 6, beginning with Section A on the history of the Great Debate. The Great Debate took place in 1920 at the Smithsonian in Washington, D.C. It was between Harlow Shapley, who we see here on the left, and Heber Curtis, pictured here on the right. They were debating about the size of the then known universe and our place in it. And the debate takes place in two parts. In the first part, Curtis argued that the solar system was near the center of the Milky Way galaxy, our galaxy, and that our galaxy was fairly small, only about 10 kiloparsecs across. Shapley, on the other hand, argued that the solar system was in the outskirts of the Milky Way galaxy, and that our galaxy was rather large, about 10 times bigger than Curtis's estimate, 100 kiloparsecs across. In Section A of the procedure, you're going to use R.R. Lowry stars to resolve this. You're going to measure the distances to globular clusters, which are distributed in a halo about our galaxy. And in doing this, you will figure out our location in the Milky Way galaxy and the approximate size of the Milky Way galaxy. Now, in the second part of the Great Debate, Shapley argued that the Milky Way was so big that it had to be the primary object in the universe. And all the other spiral galaxies, which back then were called spiral nebulae because we did not know if they were galaxies like our own, he argued that all the other spiral nebulae were smaller and distributed around us. Curtis, on the other hand, argued that the spiral nebulae were farther away than Shapley thought, and consequently intrinsically bigger and comparable in size to our Milky Way galaxy. If that's the case, that makes the Milky Way not unique, just one of countless many galaxies out there in the cosmos. In Section B of the procedure, you're going to use Cepheid variable stars to measure the distances to a handful of spiral nebulae, and you're going to measure their angular size, which you'll combine with that distance to figure out how big they are intrinsically, what their physical size is, and you'll compare that to your measurement of the size of the Milky Way galaxy, determining whether our galaxy is unique or nothing special. Okay. In the next two background sections, we'll delve into the two parts of the Great Debate in greater detail, beginning with background section B, in which we'll learn how to use R.R. Lowry stars in globular clusters to measure the size of our Milky Way galaxy and our place in it. But to do this, we need to better understand what these globular clusters are and how they formed. What they are giant clusters of stars, sometimes hundreds of thousands of stars. And they formed from a single cloud of gas, a very large, very massive cloud of gas, typically 100,000 times the mass of our sun. And these gas clouds are just borderline stable. They're not too difficult to disturb, usually through gravitational interaction with other nearby clouds. Once you disturb them, they begin to collapse. And they don't collapse down to a single supermassive star. Instead, as they collapse, they fragment, and the fragments fragment, and those fragments fragment over and over again until you have typically 100,000 little clouds, each one forming its own star and its own solar system, giving you a globular cluster. Now, if this happens in the plane of our galaxy, the plane of the Milky Way, these star clusters are pretty quickly torn apart through gravitational interactions with other clouds and other star systems. But if they form above or below the plane of the Milky Way galaxy, they're there essentially forever. There's nothing that will tear them apart. And many of these formed when the galaxy itself formed. So this figure takes place on even larger scales. Here we're looking at a handful of clouds that merge and become our Milky Way galaxy. They come together, and then the clouds settle down into a rotating disk that we see here and here. Now, as this is happening, globular star clusters are forming in these very large clouds of gas. So most of the gas settles down into a disk, but before it does that, it leaves a great many of these globular clusters above and below the plane of the galaxy. And as I said, there's nothing up there to disturb them, so they continue to orbit the galaxy today on kind of random orbits, but a distribution centered on the center of our galaxy, and the size of this distribution should be comparable to the size of the galaxy. So we can use them to measure our place in the galaxy and the size of the galaxy. And that's what we'll do. Just as we did in Lab 5, we'll use an R-Lyrae star in each of these to measure the distance to a globular cluster. We'll measure distances to about 30, randomly selected out of the approximately 150 globular clusters orbiting around our galaxy. Once we have those distances, we'll use the graphing application to make a top-down map. What the distribution looks like if we were outside of our galaxy, on top of it, looking down. It looks something like this. And in particular, we're going to find our place in this distribution, which will tell us whether we are at the center of the galaxy or off in the outskirts. And we'll measure the size of this distribution, which gives us approximately the size of our galaxy. Okay. Now, in background section C, we're going to delve further into the second part of the Great Debate, in which we're going to use Cepheid variable stars to measure the distances to and sizes of, the diameters of, spiral nebulae. But first, what are these spiral nebulae? Well, the most famous one is Andromeda. You can see it here. It's about 4 degrees across. That's 8 times the size of the moon. But it's faint, so you need to have binoculars or be looking through a small telescope to see its full extent. But if you look beyond Andromeda, you quickly realize the sky is full of these. Countless many. Here are 6 examples here. And in this lab, you're going to image a handful of spiral nebulae. And then, as we did in Lab 5, you're going to use a Cepheid variable star to measure the distance to that spiral nebula. And then you're going to load your image in Afterglow and measure its angular size. You can then use the distance that you measured from the Cepheid and the angular size that you measured from Afterglow to figure out the true physical intrinsic size of the galaxy. And you'll do that using the same geometry that we've used in so many of these labs. As you can see in this figure, the angular diameter of the spiral nebula as a fraction of 360 degrees is equal to the physical diameter of the spiral nebula as a fraction of the circumference of this large circle. That's the equation we have here. And the circumference of this large circle is just 2 pi times its radius, which in this case is the distance between us and the spiral nebula. That's substituted in here. And then solving this equation for diameter, we get this. And so you'll input the distance to the Cepheid variable star, and hence to the spiral nebula here. You'll input the angular diameter of the spiral nebula that you measured in Afterglow here, but be sure to convert it to degrees first. And then you calculate the physical diameter. You'll do this for the spiral nebulae that you observed, and then you'll look back at the diameter that you calculated for our Milky Way using R-Lyraes and globular clusters, and determine whether our Milky Way galaxy is unique or if it's typical of the spiral nebulae. If that's the case, the spiral nebulae are galaxies, just like our own, and our galaxy is not unique or special. It's just one of countless many out there in the cosmos. Okay, that's it for this video.